This video looks at the concept of integration by parts. What is it? Why do we care? How does it work? And then at the end we'll get some kind of a tool to help us out. So the goal is to be able to integrate more functions. Currently, we know how to find the antiderivative using our intuition, or the power rule in reverse, or use substitution. And if we stop there, then in the big scheme of things, the big picture is that we don't really know how to integrate many functions at all. And so there are techniques that are going to be introduced that will help us to increase our library of functions that we can find the antiderivative of. First up is integration by parts. Just so you know, here are the others: integrating powers of trig functions, trig substitution, and partial fraction decomposition. This video focuses on the concept behind integration by parts. When you learn substitution, it could have been thought of as the chain rule in reverse. The chain rule is used to be able to integrate functions that are composite functions, where you have a function inside of another function. Well, if you want to do that in reverse, if you want to find the antiderivative of such a thing, a key tool was use substitution. Well, if that's the case, then we can also draw a parallel with integration by parts. Integration by parts can be thought of as the product rule in reverse. The product rule helps us to take the derivative of a product of functions. So integration by parts will help us to take the antiderivative of it. Let's take a look at the product rule. It says, in order to take the derivative, this action, d dx is an action on what's to happen afterwards. In order to take the derivative of f times g, what we do is take f prime and multiply it by g, and then we add to that f multiplied by g prime. Okay, great. Now, what we're going to do with this statement is to integrate both sides. Integrate the left, integrate the right. Now, we know from the fundamental theorem of calculus that on the left, when you integrate a derivative, what you get out is just the integrand. And so these two cancel each other out, and so on the left hand side we'll have f times g. On the right hand side we just have two integrals. I've made them different colors here so we can identify one from the other. By convention, it's been decided that we should solve for f times g prime, the integral of that. And so we're going to do that by shipping this other guy, f prime times g, the integral of f prime times g, shipping that over to the other side, subtracting it over. Okay, so we subtract over the blue integral, that is the integral of f prime times g, and we're left with the red integral by itself on the right hand side, the integral of f times g prime. Just rearrange this so left is right and right is left, so it's normally the way we read, and it says that in order to be able to integrate f times g prime, you can instead take f times g and subtract this other integral, the integral of f prime times g. Now what we need to do is change some variables around so it looks familiar to us, but in fact this is at heart the integration by parts formula. Let's rename some things so it looks more familiar to you if you've seen it before. Get rid of the colors. We have the same statement as last time, and we're going to let u be f of x. Its derivative, du, is f prime dx. Its differential du is f prime dx. Then let's let v be g of x. Its differential dv is g prime of x dx. Going in the equation, we see that all these elements are there. F of x is u. It's multiplied by g prime of x dx. Then we have an f and a g, so that's a u times a v. And then we have an integral where we subtract the integral of g times f prime, that's v times du. So renaming these guys in this manner gives you the more familiar formula that in order to integrate u dv, you can trade it in and instead deal with u times v minus the integral of v du. That's the more familiar version of integration by parts. Here's the issue though. We need to be able to choose u and choose dv. The integral that you are given will be the integral that's on the left, and one part of it will be called u, the other part will be called dv. And the point is that you're going to trade it in for this integral that's on the right, v du, the integral of v du. So we need to figure out, well, how can we go about doing that? How do we know which one to make u and which one to make dv? The one integral that you have, integral of u dv, is traded in for the integral of v du. It really makes sense to do it only if it's going to be something that's simpler. If you trade in for something that's more complicated, then you're not, progressing. And so what we need to do is figure out how can we make sure that the one that we're trading in for is simpler. And here are two ideas that will help you out. When it comes to u, we should choose u to be a function that becomes simpler when differentiated. Look at the difference here from what you have and what you're going to trade in for. What you have has u. What you're going to trade in for has du, the derivative of it. And so we need to make sure that it looks simpler when differentiated. We'll see what that means by looks simpler, but yeah, it needs to become simpler. If that means like a square becoming a first power or a cube becoming a square, then that's what we have in mind. The other part of the integral is dv. You're given this integral u dv, and it traded in for this integral v du. So dv gets traded in for v. That's working it backwards. That needs to be the integration. To go from dv to v, you integrate. So you need to make sure that the part that you choose dv to be needs to be something that you can actually integrate. Otherwise, you're not getting anywhere. So these are ideas to help you out. And we have the formula. We know where the formula comes from. We have mechanisms. We have ideas to help us along the way. Lastly, let's discuss a tool that will help you figure out what to choose u to be. It's a mnemonic. It's a hierarchy at first here. Part of it's a hierarchy, and it's going to help you figure out what to choose u to be. First on the list, logarithmic functions. If there are any logarithmic functions in the integral that you're thinking about doing it with integration by parts, you must let u be that logarithmic function. In the absence of logarithmic functions, next on the hierarchy is inverse trig functions. If there's inverse trig functions and no log functions, then you should choose u to be the inverse trig functions. Okay. In the absence of log functions, in the absence of inverse trig functions, then you should choose u to be an algebraic function. Now, you might not have seen this written like this. When we think of algebraic functions, mostly we think of just polynomials, but we'll be short-sighted if we were to call this just polynomial functions, because there's other functions that we need to include into this mix. Any kind of a root of a variable or anything like that, any power on a variable is called an algebraic function. And so that would be next on the list. It's really here that the hierarchy ends. There's two more to come, but they're pretty much interchangeable. One's not any better than the other. One doesn't come before the other. The hierarchy ends here, and the last two are trig functions and exponential functions. These two guys are interchangeable. So if there's exponential and trig, it doesn't really matter who you're going to choose to be u and who you're going to choose to be dv. Okay, so this spells out the word liate. If I were to interchange them and put the e and t, it'd just be a harder word to pronounce. And so that's why I chose t before e here, so you can at least verbalize liate as your mnemonic, and that will help you to decide how should you go about the choosing of what u should be. And this ends our concept video.